Hi everyone, I appreciate you viewing this part of the lecture on D2L. I'm hoping we don't get too far behind with another snow day, and so I wanted to just be able to cover some things online with you so that we can kind of jump back in next week. So we'll start on Chapter 3, the chemistry of food composition today, and then we'll get through pretty much talking about water, and then we'll start up on the other nutrients next week. We'll also kind of touch back on chapter 2 next week since we really didn't get to cover that because of the snow day last week as well. So we'll go ahead and get started. Um, so just to kind of review back to nutrition. So in this chapter, we'll cover all of the essential nutrients and how they kind of play a role in our body, but also in our food supply. So remember, nutrients are those essential compounds we need to get from food in order to really nourish our body. So to help with growth, to give us energy, to help with overall function of our body. So we have those 6 essential nutrients. So our macronutrients, so carbohydrates, lipids, and protein. And remember, those are energy providing, so they give us energy in the form of calories. We then have our micronutrients, so our vitamins and minerals, right? And then our 6th essential nutrient is water. And so water is what we'll talk about in this part of the lecture primarily. So our body is made up of 60 to 70% water. And we'll also see that our foods have a high percentage of water as well. And so water is not only essential for our life, but also essential in our food supply and in the functions of our food in cooking. So water is our simplest of all of our nutrients, but yet we consider it the most important. So we need water in our body as a transport mechanism in our blood, so it is going to transport our nutrients and our essential kind of life-giving compounds. It also acts to excrete nutrients and byproducts of metabolism. It helps regulate body temperature. But water is also going to be important in the function of food. So water content in our food supply and in our individual foods can really vary widely. So you can see in this figure here, our fruits and vegetables are going to have the highest percentage of water. So tomatoes, watermelon, you probably often think of as being high in water content. We then have some foods that are much lower. So our oils, for example, have a very low content of water, as well as some of our dried foods, our grains, our beans. Water is a very small molecule consisting of just 3 atoms. So it has one oxygen atom with a -2 charge, which is then flanked by 2 hydrogen atoms, each with a positive charge. So overall, water has a neutral charge. It's neutral again because it has those 2 hydrogen atoms, each with that positive charge, and that one oxygen atom with those two with the 2 negative charge. So these atoms balance each other out, making it neutral. So this results in a water molecule that has a negative pole. So that negative pole driven by that -2 charge on that oxygen atom, and then a positive pole. So this makes it what is known as dipolar. So this dipolar nature gives water the ability, gives really water many of its characteristics. So the hydrogen of one water molecule is able to bind with oxygen of another water molecule. These bonds are known as hydrogen bonds. So it forms a hydrogen bond between water molecules with oxygen of one bonded to the hydrogen of another. So these bonds are weak and they're able to be formed and reformed, but energy is required to break them. And because there's so many hydrogen bonds within the large water structure between each water molecule, it needs a significant amount of energy. And this energy is given in the form of heat. So it's either that loss of heat or addition of heat, which allows it to move through its different stages. The energy from this heat is measured in the form of calories or kilocalories. So we can have water that is either bound or free within food. So free water is easily separated from food. So we usually see free water in our fruits and vegetables. So it gives it that juiciness that we see. So free water can dissolve solutes such as salt or sugar within the food. We then have bound water. So this is water that's been incorporated into the chemical structure along with some other nutrients. So bound water isn't easily removed. We can't easily dry it out or freeze it. And it's not able to dissolve any other solutes, so none of those sugars, salts, or acids. So the amount of energy that's needed to really raise that temperature, so to raise the temperature of 1 gram of water by 1 degree Celsius is known as the specific heat. So water has naturally a very high specific heat, and that makes it unique compared to other compounds on Earth. So compared to different metals, such as like aluminum or iron, water specific heat is actually much higher. So we give water a specific heat of 1. And so we really use water as a standard, and we compare our other compounds to water. So here's an example. If we expose, for example, this metal spoon or this wooden spoon to the same amount of heat as we expose water, the water is still going to be lukewarm. We could put our hand in it, for example, and we wouldn't get burned. But if we were to touch that wooden spoon, it might be a bit hotter than that lukewarm water. If we were to touch the metal spoon, we might actually burn ourselves. Okay, so water is able to absorb that heat and hold on to it without actually heating it to the point where we can't touch it. This high specific heat is really related to its molecular structure and the bonds that need to be broken in order to really heat it up. So because it takes more energy, because of that high specific heat, water also has a higher heat capacity. So it can hold on to more heat because we need to expose it to more in order to actually heat it up or make it warm. So again, this heat that we expose it to is measured in the form of calories. So when calories are absorbed within the substance or released from the substance, we see a change in state. So as we add calories or heat to water and it absorbs it, we see it changes state. For example, with solid ice, if we expose it to 80 calories per gram of water, it absorbs that heat and is able to change a state and change into a liquid state. We can also release that heat. So we can then go release that 80 calories per gram and go from a liquid state back to a solid state. Same can be said when moving from a liquid to a gas state or the opposite. So we would add that 540 calories per gram. This would be absorbed by the liquid or by the water, and we would change into a gaseous state. We could then also release that 540 calories per gram and go from a gas back to a liquid. So it's going to be important to know the amounts for water in which, the amounts of energy in which we add or are released when moving from one state to another. So I would be familiar with the 80 calories per gram going back and forth from solid to liquid or liquid to solid. And I would be familiar with the 540 calories per gram when going from a liquid to a gas or a gas to a liquid. So again, when we add in that heat or we release that heat, we're changing the state in which the water is in. So this change in state isn't necessarily related to breaking of any sort of bonds. It is instead related to the movement of the molecules. Right. So it's because of these hydrogen bonds between the water molecules that it takes more energy or more heat to essentially heat water or have it change states than it does any other substance. So again, that's because of that water's high specific heat. So this makes it unique as well as to the amount of energy it takes to reach its specified freezing, melting, or boiling points. So when we expose water to heat, or we have it release energy in the form of heat, for example, again, we're affecting the movement or the kinetic energy. So let's think, for example, going from a liquid to a solid. So as the temperature lowers, we're lowering this kinetic energy or the movement of the water molecules. So kinetic energy is simply the energy that's associated with motion or with movement. So as we lower the kinetic energy through the lowering of the temperature, our water molecules slow down. So as they slow, they're able to kind of associate better with one another. They're able to line up closely and form a solid structure, so in the form of ice. Okay. As we heat up water, so if we go from a liquid to a gas, we're applying more heat. Right? We actually have these molecules moving further apart from one another. So there's more movement. They're not able to align up or associate with one another as well as they were in a liquid or a solid state. They're actually able to escape one another, okay, and form a gaseous state. So again, it is the hydrogen bonds that are being affected, and it's the movement. Okay. So why is this important? Well, we know that, the state of water is important in our food supply and our cooking methods. So if we first kind of look at what the freezing point is, so the point at which water releases at 80 calories per gram and goes from a liquid state into a solid state. So as we know, as it's like 15 degrees outside right now, water has hit that freezing point and we have ice on our roads. So this can happen at 32 degrees Fahrenheit. So 32 degrees Fahrenheit is the freezing point of water. So that temperature where liquid is able to turn to a solid. Right. So this is done by releasing that 80 calories per gram of water. And this is known as the heat of solidification. So the heat of solidification is that amount of heat or the amount of energy in the form of calories that's released for a substance to turn into a solid. So for water, it is that 80 calories per gram. Something that's a little bit different about water is that it actually expands and becomes less dense when it freezes. So you can think of this in a few different scenarios. So the first might be a freezing of our pipes. So we know that if water freezes within our pipes, it can cause our pipes to rupture. And this is because water actually expands, becomes less dense, can cause our pipes to rupture. When we're thinking of food, for example, we might think of different molds that we make ice or popsicles out of. They're generally kind of pliable rubber molds, and they have some give to them so that as whatever we're trying to freeze freezes and it expands, the product or whatever that mold is able to expand as well. This is also going to be important when we're thinking about water within our foods. So we have, as I mentioned with fruits and vegetables, a high free water content. So water is within the cells and outside of the cells. Well, if water expands as it freezes, so in the case of a fruit or a vegetable, it actually can rupture the cell wall of the fruit or vegetable. And so this really causes, in a frozen fruit or vegetable, an inferior texture after it's cooked. So we've destroyed that cell wall that really gives that food some stability and its structure. And so we might have more of a mushy, less kind of crisp texture once we thaw it out. Another kind of important characteristic of water related to freezing point is that the addition of any sort of solute, so for example salt or sugar, actually lowers the freezing point. Okay. But we can, if we expose it to too much, or if we add too much salt or water, we've actually really slowed that freezing process down now. So we might use the lowering of this freezing point in some of our cooking methods. So an example might be in ice cream. So when we make ice cream, we want to freeze it quickly. This gives it a smoother texture. The issue here is that the sugar in the solution actually depresses at the temperature at which it freezes. So it takes longer for that ice cream to freeze, which would make kind of a more inferior texture of ice cream. We want it to freeze quickly. So what we do is, as we are creating that ice cream or making that ice cream, we place it into a container that is both agitated and then chilled within a mixture of salt and ice. Okay, so remember, adding salt to water, or ice in this case, is going to lower the temperature, lower that freezing. Because it lowers that freezing temperature, we now have the ice at an even colder temperature, which then speeds up the ability of that ice cream to freeze. So we can freeze that ice cream quicker by give it that smoother texture that we all desire. So now that state of moving from a solid back to a liquid. So we're going to be absorbing that 80 calories per gram. So our melting point, pure water is able to change from that solid texture to that liquid at 32 degrees Fahrenheit. So we're returning that 80 calories per gram of water to the water, and we're allowing our water to go from a solid state to a liquid state. Now something to notice here is that when ice melts, there's really no change in temperature. So think of a cooler, for example. If you have a cooler full of ice and it melts, that water is still extremely cold. However, it's in that liquid form now, but it is the same temperature as it was. It hasn't warmed up at this point. That's because that amount of energy that we're giving, or that heat that we're exposing the solid to, is all used to change states. So there's no change in actual temperature because that heat or that energy was all used just to change the state from solid to liquid. So we actually haven't been able to even heat the water at this point. So this is known as latent heat. Okay. So it's that energy per gram that is absorbed, okay, or emitted in the case of going from liquid to solid as the substance changes its states. But again, it doesn't actually affect the temperature of the water in this case. So then our last state is moving from a liquid to a vapor or a gas. So this is known as boiling. So we reach our boiling point when we have bubbles starting to break the surface of the water and we're creating steam. So at sea level, and this is going to be important when we're talking about pressure, so at sea level, this occurs at 212 degrees Fahrenheit. So at this point, at this 212 degrees Fahrenheit, the addition of any additional heat isn't going to change the temperature. So instead, it is going to release steam. So water, pure water, can't get any hotter than 212 degrees Fahrenheit when at sea level. So in order to go from this liquid state to this gaseous vapor or gaseous state, we need to add 540 calories per gram. Okay. And so at sea level, we have vapor pressure exceeding our atmospheric pressure. So essentially what we have is we have the ability of the water to release the steam. So as water boils, it is trying to the steam is trying to escape. Once that vapor pressure, so the pressure of that steam, exceeds the atmospheric pressure, it is actually being able to be released at this point. So we'll have that steam released into the air. So think of vapor pressure as essentially kind of pushing against that atmospheric pressure. And once it can exceed it, we have that steam released. So we can have changes to the atmospheric pressure which are going to affect the amount of heat we need to add in order for vapor pressure to exceed the atmospheric pressure. So again, adding additional heat isn't going to increase the temperature of pure water at sea level. So 212 degrees is as hot as we're going to get. It's also not going to affect the cooking of our food. So this is why typically once we are at a boiling point, we'll turn that heat down to more of a simmer. And we'll talk more about that when we talk about moist heat cooking methods. But again, it's not going to get any hotter than that 212 degrees Fahrenheit. So I mentioned sea level a few times, and this is because a change in elevation changes the atmospheric pressure that's pushing down on the Earth's surface. So an increase in elevation causes a decrease in boiling point by 1 degree per 500 feet. So again, this is because there's less air, there's less atmospheric pressure pushing down on the Earth's surface, and therefore our water can boil at a lower temperature. So the steam is faced with less resistance than it is at sea level. So in the mountains, water boils at a lower temperature than it does at sea level because that steam has less resistance against it. So generally, when looking at recipes, for example, once we're at 3,000 feet or higher, we might, this will lower that boiling temperature and is going to significantly affect the ingredient kind of interactions. And so you might see changes to your recipes noted when you're at this kind of elevation. So we can create artificial pressure in order to kind of speed up our cooking time. This is going to be done through the use of pressure cookers. Okay. So the purpose of a pressure cooker is to add that 15 pounds of atmospheric pressure and then trap it. So by doing so, our water needs to heat up more to kind of combat that additional pressure and release that steam. So our boiling point goes from 212 degrees Fahrenheit up to 250 degrees Fahrenheit. So we're cooking at a much higher temperature, meaning we're really speeding up the cooking process. Okay. So this is the popularity of those Instant Pots that are currently available, which is just kind of a modification to the original pressure cooker. But again, it's adding that additional pressure, which requires us to cook at a higher heat in order to boil. So it speeds up our cooking times. We also know that the addition of solutes, so for example, a solute is going to be something that can dissolve in water, for example. Water being the solvent in a solution, what the solute is dissolved in. So for example, most commonly we would think about sugar or salt being a solute. And this can also affect the boiling point. Okay. So adding solvents to water, such as the sugar or salt, we'll see an increase in the boiling point. This is because the salt or the sugar attracts or binds water. And so the vapor pressure is decreased, and so more energy is required to increase the point at which water boils and converts to steam. So the greater concentration, the greater the amount of, or the more solute or so salt or sugar that we add, the higher the boiling point. So we will talk more about this in our second lab, actually, where we'll look at how different solutes affect the ability for water, or the solution in this case, to boil. So we'll see this in action. So this is especially true, or mostly true, when we are able to form a true solution. So a true solution is in which a solute is able to completely dissolve within that solvent. So in which we can completely dissolve that sugar or that salt within that water, for example. And so we're looking at small molecules that are able to form a true solution. Interestingly enough, and we'll see this again in the lab, salt is going to have twice the effect on vapor pressure as sugar does. This is because salt is sodium chloride, and so salt can separate out in solution. So we have that sodium associating with water and that chloride associating with water. So those two ions separate out, are able to bond with the water molecules and affect the vapor pressure. So a true solution is one type of dispersion. So dispersion is really a mixture that contains particles dispersed within a continuous phase. So these particles, they can be solid, they can be liquid, or they can be gas. And then they're dispersed within another solid, liquid, or gas. So a true solution is a type of dispersion, typically where we have solids dispersed within that continuous phase of liquid, so salt or sugar within the water. So we then have different types of dispersions that we have in our food supply. Okay. So some, for example, a colloidal dispersion. So some particles aren't able to fully dissolve. So a colloidal dispersion has colloids, or starches, gums, some proteins, for example. They can't truly dissolve in a solvent because they're too large. So they can't form a true solution. But at the same time, they're not large enough to fully precipitate out. Okay, so they're remaining kind of unstable. They don't really noticeably affect the dispersion's freezing or boiling point. So there's a few different types. An emulsion, for example. We'll talk about emulsions more when we look at talking about fats and oils. So they're dispersed within one another, but not fully dissolved to form a true solution. A gel is another example. It's a liquid in a solid dispersion. And then a foam might also be an example in the case of a whipped cream. So it's a gas in a liquid dispersion. So whipped cream or whipped egg whites, so we're whipping that air within that liquid. You may also have then what's known as a coarse suspension. So a coarse suspension also is particles that are too large to go into solution. So they're really suspended out in the solvent. Or within that continuous phase. So example, cornstarch within water. That starch, it floats. It doesn't dissolve within, but it floats within that water. So again, examples might be cornstarch in water, cornmeal in water. So these starches or gums or larger molecules. And they're not going to cause any sort of change to the boiling point. So So we have a couple other characteristics of water. So most water isn't necessarily pure. Water might contain dissolved gases, different minerals, salts, soil, okay, that might be dissolved within it. So the type of minerals and the amount of minerals that are in water determine whether or not it is hard or soft. So hard water contains more calcium or magnesium, and soft water contains a higher sodium content. So hard water, we're typically going to see those rings on our bathtubs, our toilets, leave salts on or spots on glasses, sediments within our laundry. Okay. Soft water, we aren't going to see these things. So this is kind of the principle of a water softener, is to exchange sodium for calcium and magnesium ions. So to increase that sodium content and kind of lower that calcium and magnesium content within the water to make a softer water. So we don't see a lot of effect as far as our food supply goes or our cooking methods go related to hard and soft water, but it's just something to be aware of. So when it comes to water and food's perishability, we know that a food's water activity or the availability of water, so the amount of free water within the food, really determines its perishability. So bacteria need water in order to grow. And most foods aren't going to support bacteria growth if their water activity is below 0.85. So pure water has a water activity of 1.0. So therefore, foods that have a high water content, such as milk, meats, fruits, and vegetables, are going to be more prone to spoilage than drier foods like our nuts, our beans, or dried fruits. And so once deterioration of the food sets in, the petrifying food is also going to release water, which is going to fuel the growth of that microorganism. So kind of once that spoilage begins, more water is released, speeding up the decay. And so we can lower the water activity by adding substances. So for example, adding salt or sugar. This is going to bind to that free water and reduce that water activity by increasing the amount of bound water, making it kind of unavailable for the growth of bacteria. Right. So that's where I'm going to stop. I appreciate you guys viewing this. Just a reminder, your MindTap assignment is now open, and so that's going to be due next Wednesday. So this will give you a chance to kind of review the first 3 chapters as well, and we'll finish up this last part of chapter 3 next week. And so you'll have a chance to kind of finish that up before your assignment's due, but you can go ahead and get started. And it is open now. And so I will see you guys next week.